Hello everyone, welcome to our presentation on object classification using machine learning. I'm here representing team IJ. Today we will be exploring how image classification techniques, specifically those developed through our work with the CFA dataset, can transform ordinary security camera into intelligent monitoring system. Our project sits at the intersection of machine learning and practical application, taking powerful image classification algorithms and applying them to solve real-world problems in home security. We will demonstrate how the same principle that allow computers to distinguish between car, cat in benchmark dataset can be extended to create a security system that recognizes package delivery, identifies strangers, and detect unusual behavior patterns. Over the next few minutes, we will walk you through the problem we are addressing, our technical approach using predictive modeling, and the business value our solution creates for homeowners. Let's get started by looking at why traditional security cameras are failing to meet modern homeowner needs and how machine learning can bridge this gap. Let's examine the fundamental problem with traditional home security system that our machine learning solution aims to address. First and foremost, traditional security cameras only passively record without any intelligent analysis. They capture footage but lack of ability to understand what they are seeing, essentially functioning as digital witness rather than preventative tool. This leads to our second critical issue. Basic motion detection generates an overwhelming number of false alarms. More than 75% of alerts. Every rustling leaf or passing car triggers a notification flooding users with irrelevant information. The natural consequence is what security experts call alert fatigue. Homeowners become desensitized to constant notification and eventually start ignoring them altogether, defeating the very purpose of having alerts. Current system cannot distinguish between important events and trivial movements. A delivery person at your door receiving the same alert priority as branch swaying in the wind. There is no ability to recognize specific objects or people, packages, or pets, or register simply as motion detected. This lack of specificity severely limits the system's usefulness. Let me introduce our intelligent security solution. Our system transforms standard camera into smart security devices using image classification technique. First, advanced object detection that identify over 50 common objects with 97% accuracy, distinguishing package from pet from people. Second, person recognition that differentiates between household members, regular visitors, and strangers. Third, behavioral analysis that spot unusual patterns like loitering, someone wandering in one area for over 3 minutes. The second part of our solution focuses on delivering intelligent notification that homeowners actually pay attention to. Our smart alerting system prioritizes notifications based on security relevance. A stranger lingering by your door gets higher priority than neighborhood cat walking through your yard. Speed matters in security. Our system delivers alert within just 1.8 seconds of event detection, giving homeowner maximum response time for any situation. The proof is in the engagement. Users show a 68% higher response rate to our alert compared to traditional system because they trust that our notification matter. The third component of our solution eliminates the tedious task of manually reviewing security footage. Our intelligent indexing system automatically categorizes and timestamp all events, creating a searchable database rather than our off-raw video. This search efficiency is game-changing. It reduces footage review time by 83% compared to traditional manual method. What used to take an hour now take just 10 minutes. We have enhanced usability through data visualization with timeline view featuring color-coded event for quick visual scanning, green for normal activity, yellow for unusual pattern, and red for potential security concerns. For our home security project, we are building on the foundation of CFA 100 dataset. which provide an excellent training ground for image classification technique we need. C5100 consists of 60,000 color images, each a small 32 by 32 pixel categorized across 100 distinct classes, which these images are compact compared to security footage. They create an ideal environment for developing our classification algorithm. The dataset is structured with 50,000 training images and 10,000 test images, allowing us both train our model effectively and reliably evaluate their performance. What makes C5100 particularly valuable for our security application is its hierarchical organization. The 100 object categories are grouped into 20 superclasses. This structure mirrors how we want our security system to recognize both specific objects and broader category of interest. Let me walk you through our exploratory data analysis of C5100 datasets, which form the foundation of our smart security system. For this project, we are working with C5100 dataset, which we have access through TensorFlow Keras dataset interface. Unlike the simpler C510, we are using the more complex version with fine-grained levels that include 100 distinct categories. This increased granularity will help our system distinguish between more subtle differences in objects and people. Our initial exploration focused on understanding the dataset. We are examining the shape of our array to confirm what we are working with. To verify the dataset integrity, we check the number of unique classes using NumPy's unique function on our training levels. This confirms exactly 100 distinct classes as expected, ensuring our dataset is properly loaded and structured before we begin model development. Our exploratory data analysis reveals key patterns that inform our security approach. The C5100 images are small 32 by 32 RGB samples, covering 100 diverse categories from everyday objects to animal to people, mirroring what our security system needs to recognize. The labeling structure assigns each image numerical labels 0 to 99 with corresponding human readable class name, which we will adapt for near security notification. Importantly, C500 is balanced with equal sample per class, helping prevent algorithm bias during training. This represents a classic multi-class classification problem with 100 classes, directly analogous to the security challenge of distinguishing between different objects and events in home environment.
And these are the models that we're going to use to compare the performance on image classification tags, which are LexNet, ResNet, and K-nearest neighbors, or it is KNN. The first two are deep learning models, and the last one is machine learning models. And this is the architectures of LexNet models. It consists of convolutional layers to extract the local features of the image, then it passes to the fully connected layers to classify the class. Now this is the architectures of ResNet models. As you can see, it's become more complex, but it has almost the same layers as the LexNet, and it also has short connection that will add the features before the convolutional layers to the output of convolutional layers. Finally, it is K-nearest neighbors, and this is just a brief ideas of how KNN works. So first, we're gonna pass our image data through the PCA, then we're gonna fit it in the KNN models. And when we have the image that we don't know about the class, we will pass it through the PCA again and fit it in the KNN models. And we're gonna select K nearest point to the input image. And finally, we're gonna classify the class of the input image to be the majority of the K point that we selected. So how are we gonna train the models? We separate it into deep learning models and machine learning models. So let's start with the deep learning models. First, we're gonna separate the data into train, validation, and test dataset, and we're gonna pre-process the image by resizing it, and we're gonna do the hyperparameter tunings on parameter weight decay using random search, and then we're gonna train and validate using loss function as the cross entropy loss, and we're gonna test using the defined matrix and visualize using TensorBoard. Now for training machine learning models, we perform almost the same steps. We separate the data, reprocessing the image, but this time we use principal component analysis, and we also do the hyperparameter tunings, but on a different parameters, which are neighbors, weight, algorithms, and distance function. We also perform the cost validation using K-fold and feed the data to the KNN models and test, then we visualize it. And these are the metrics that we're gonna use: precision, recall, F1 score, false acceptance rate, and true acceptance rate. These are the result of ResNet model that we visualize using TensorBoard, and we log it for each epoch. As the epoch increase, the F1 score, precision, recall, and true acceptance rate are increasing, and false acceptance rate and loss are decreasing. This image also shows us that the models with weight decay of 0.0001 is the best model to perform this task. And these are the results of the AlexNet models. Also, it shows the same trend as the ResNet model. And for KNN, we don't need to train for multiple epochs, so we don't have the graph, and this is the result of the KNN models. We also do the visualization to compare each metric on every model that we have, and the results show us that ResNet models is the best model among these three on image classification tags, and KNN is the worst, even though AlexNet models has the highest false acceptance rate. And this is the demo of ResNet models on classifying the image.
Let me summarize how our analysis of the CIFAR 100 dataset directly translates to solving real business problems in home security. We have identified that traditional home security systems suffer from excessive false alarm, lack of intelligent object recognition, and create information overload for users. Our exploration of the CIFAR dataset with their cohesive classification capability across 10 to 100 category provide the perfect foundation for addressing this exact pain point. The CIFAR dataset with their structured approach to classify diverse objects ranging from vehicle to animal to people mirror precisely what an intelligent home security system needs to identify. While working with small 32 by 32 RGB image, we have developed techniques that will scale the high resolution footage from security camera. Our exploratory data analysis reveals several critical insights. First, the balanced nature of CIFAR datasets has allowed us to train our model without bias to a particular object. Second, the multi-class classification approach we have perfected will enable us to provide homeowners with specific actionable notifications rather than generic motion alerts. By extending the classification capability we developed with CIFAR, our smart security system will reduce false alarm by over 70%, provide specific object and person recognition, and create searchable event logs that save homeowners hours of review time. The technique proven to benchmark dataset will translate directly to real-world security monitoring.
And today, we compare three models, which are AlexNet, ResNet, and KNN models on the image classification tags. And the results show us that the ResNet model has the best ability to classify the image in the CIFAR 100 dataset. Thank you for listening.